So when I was learning the concept of groups, what helped me the most was to look at examples and try to show one way or another whether a particular set is a group or it's not a group. So maybe we'll go through a few of those. I see one of these review questions for this chapter. It is review question 2 here. It says, show that 5 and this weird z here, meaning the integers, it's going to give us some set notation here. So 5 in, so the set of all numbers 5 times n such that, this colon here, such that n is in the integers. And there may be a slight delay on the YouTube live, but it should pop up pretty quickly what I'm writing here. So show that this thing here is a group under addition. Okay, so a group under addition. Now, anytime we have a group, if you go to the definition up at the top of this chapter, a group is a set, and it doesn't necessarily have to be numbers. So that's an important thing to note about groups, is that it is just any set. It doesn't necessarily have to be numbers. It could be a set of rotations, for example. But it does have something in particular, and what it has is a binary operation. And in this particular case, we have addition here being our binary operation. Okay, so binary here meaning it's going to give us an output. So binary means yes or no. It's kind of like computer language, 0 or 1. We have a binary operator. Okay. And then for this 5z here, so we're trying to figure out if it's a group under addition. So the operator in question being addition, and this is what you would typically think of. So this is a nice example because in this case, addition is going to work exactly how you would expect it to. In some groups, addition will work maybe slightly differently than it would in this case. But because we're working with familiar whole numbers, it's going to work out pretty well. Okay, so to show that it's a group under addition, we have to show these properties here. So we have the 4 properties. We have closure, so I'll say A, closure, B, we have associativity, or we can say that it's an associative group, an associative set for short. It has to have an identity. An identity in reference to that operator. And then it has to have inverses. Okay, so you'll notice here that it doesn't require commutativity or being abelian. So you'll notice a little bit further down, we talk about commutativity and abelian groups. And commutative groups are actually a very special kind of group. So there's actually groups in general are not guaranteed to have this nice property. It turns out with the integers, we do get this sort of nice property. Okay, let's see. So before we go on, let's talk about each one of these. Okay, so talking about closure, this idea of closure, it means that if I take any two what we call elements, let's say A and B, if we apply that operator to those two elements, so in this case that would mean to add A and B, we will never have it happen, so I'll draw in red here. It'll never happen that A plus B falls outside of that bubble. So in red here, this is just demonstrating that won't happen as long as you have closure. Okay, and so I'll continue along just sort of with this brief overview of these 4 properties here, and then what we can do is we can get into actually showing that this is the case for 5z. And it really helps to start to understand these properties by showing that they are true for a wide variety of different sets. There may be examples in your textbook where you actually use things that are not numbers. In this case, it's rather nice because we're working with integers. And things tend to work very nice with integers in general. But later on, what you'll see is that we actually have groups where the elements are, say, matrices, right? So like a matrix. And in that case, things start to get a little more strange. The way that you define your operations gets somewhat more exotic. And then showing these properties here. So then showing the closure, the associative property, the identity, and the inverses, it becomes a little bit more involved, but that's not a bad thing, because what that means is that you gain a much deeper understanding. So my suggestion is always, in learning a new concept, to try to look at it from as many angles as possible. So let's continue with this overview here, and then we'll kind of dive into that, and I can provide some practice problems that will help kind of deepen that understanding. Okay, so associative property. What are we talking about when we talk about associative property? Let's pretend that we have another element here. I'll sort of zoom in momentarily. Let's say we have C in here. So we have A, B, and C within our bubble. Okay, this is our 5z set bubble. Now, if we wanted to add A, B, and C, well, what associative property says is that it's not going to matter the order that we do this in. So we can do it in the order of adding A and B first, and then adding C, or we can add B and C first, and then add A. Okay? And this is a property of that binary operation on this set. So I want to sort of emphasize all of these properties are in reference to whatever operation we're talking about. Now, it may not be the case that these properties hold for a different operation. So if we defined a different operation, say multiplication, some of these properties may break down. And so just because we can say something in reference to the addition operation, it doesn't mean that we can say it for any other kind of operation. Okay. So that's associative. Then let's talk about this identity here. Okay, so identity, what that really means is it's an element of the set, in this case 5z. Now let me zoom back into our diagram here. Let's pretend we just have A, and then here I'm going to call this I. So I'm going to call this element I. And there's different notations we can use for this. I is sometimes used. I think E is used commonly in some textbooks. But this identity element, what it says is that when I apply the operation, in this case addition, to the identity element and some other element, in this case A, so A plus I, what it's going to do is simply give me back whatever element I'm applying that operation to, in this case A. So that's the identity. It means one way to think of this and remember it is that the identity element retains the identity of whatever element you are applying the operation to. Okay, in this case, A plus that identity element is going to give me A back. Now, of course, we know because we often work with the integers that this I, what we typically call I, is 0. Exactly. So in this case, our identity element for addition is 0, because if you add 0 to anything, you simply get that thing back. Okay, so that's what identity means. And you can sort of imagine what that might look like with multiplication as opposed to addition, right? Exactly. Exactly, yep. So that's identity. So it just means that we want an element within that bubble that's going to have this property. Okay, and you'll kind of see later on as you dive into group theory that the identity having that property opens up sort of a number of paths that allow groups to function in particular ways. It's not quite clear when you look at the integers, but when you start looking at a large number of examples, then it becomes sort of clear why we like to have that identity property within groups. Okay. Now inverses, so what inverse means, it's related to identity in this way. So let me clear some of this out. Okay, so I'm again going to give us in A here, I'm going to give us our identity again, but now I'm going to add a new element. And what I'm going to add here, I'll call the inverse of A. And how we typically denote that is just like this. So we typically denote it as the element raised to the -1 power. Okay, and an inverse, so A to the -1, we call the inverse of A because if we apply the operation to A and its inverse, what it's going to do is it's going to actually give us the identity. Okay, and so in some sense, this inverse element of A is sort of exactly what it sounds like, right? So it's kind of like the opposite or the inverted form of A, so that when you apply that operator, you're getting exactly the identity. Okay, it sort of undoes whatever A is. Okay, so that's kind of an overview of these 4 properties we like groups to have. Okay, and then you mentioned commutativity earlier, and that is a very high value property that we like groups to have. And there's actually the field of abstract algebra splits, as you study it more, it splits into 2 sort of domains. One of them being what we call commutative algebra, and the other being what we call non-commutative algebra. It turns out that commutative algebra is, in a sense, easier to work with than it is to work with non-commutative algebra. Because commutative algebra, those type of sets tend to operate in ways that we would expect. Non-commutative algebras can get pretty exotic. Okay, so then that gets to the question, how do we actually show that 5z is a group? All right, so what we'll do is we'll go through each property. Now I'll write out again what is 5z. This is going to come in handy. 5z is just defined as the set of all integers in multiplied by 5. Okay. And then the first thing, so typically whenever we show something in mathematics, we call this a proof, right? So The way that we want to go about that is we'll say proof. So we'll tell the reader that we're going to give them a proof of something. And it's customary to state what it is that you're trying to prove. Okay, so the way that we typically do this is we say WTS. WTS means want to show. Okay, we want to show that 5Z is a group under addition. All right, and then let's see here. And then the first thing that we'll show here is closure. Okay, and then how are we going to go about showing closure? So what exactly was closure again? So closure meant that if I add two elements within 5Z, I should get something back that is also in 5Z, right? Oh, the first thing I'm going to do is give us some things to work with. And the way that we do this in mathematics is we say let, and then ... whatever it is that you want to sort of conjure up, that's what we're going to do. Okay, so I'm going to let A be an element of 5Z. I'm also going to let B be an element of 5Z. And essentially what this means is that I'm sort of conjuring up some concrete things that we can work with in our proof. Okay, so I think what you said is along the right lines, so here's what we'll do. We have A and B, we have two elements. We know that we want to be able to add them and get something back that's also in 5Z. And that's our goal, is to show that that's the case. So what we'll do is we'll take this A and B in 5Z and we'll add them up. So we'll say A plus B. Okay, now if A plus B is an element of 5Z, then we have closure, right? Because I've taken an arbitrary A and an arbitrary B. Both of them are elements of 5Z. We don't know exactly what they are. But if we can show that given any two elements of our choosing, they're going to remain an element of 5Z when we add them, then we're done. This is a sort of an abstract concept in proofs. All right, so we want to show that A plus B is in 5Z. So we'll take that, but what do we also know about elements of 5Z? Let's go back up to our definition here. We know that an element of 5Z has the form, let me write, it has this form here, 5n. Okay, so what I'll do now is I'll rewrite, I'll sort of reframe this A and B that I've created to hold this form. Okay. Yeah, are you back? Okay. You should also be able to go back and rewatch the video. Yeah. So what I'll do is I'll leave these posted for now, and then what I may do is edit them and kind of re-upload a more concise video. But you should be able to go back. You got it? Okay. Is it, yeah. Okay. So I'll take this A and B that I've created here. Okay, good. Yeah, so this A and B here, I'll sort of think of them in terms of the definition of my set 5z. What that means that I can do is I can say that A equals, let's say 5, we can pick any letter we want, let's say 5C, and B equals, let's say 5D. And the reason we know this is the case is because that falls under our definition here of 5z. Yeah. Okay, so I'll rewrite this now. So I'll take actually 5c and add that with 5d. And now what we can do is actually get us somewhere that will show that this is an element of 5z. Okay, and how would I do that? Well, I can simply take out, I can factor out a 5 from each of these components here. And what that'll do is that'll give me 5, right, exactly, 5c plus d. Okay, and now this we can say is an element of 5z. And why is that an element of 5z? Because c plus d is an element of the integers. And if we look back one more time at our definition of the set 5z, all that we require is 5 times some integer, right? And we know that if we add any two integers, surely we will get an integer. Okay, so what I'll do here is I'll draw a box and sort of shade it in. And what this denotes is that we're done with that part of the proof. Okay, so this gives us closure, and then we're good. And then the next thing we want to show, so I'll check off closure. We want to show now associativity. Okay, so going down here, the second part, associativity. So we want to show WTS, associativity. Okay, and then what does associativity mean again? It means that if we add any three elements, it won't matter which order we add those things in, right? So if we add the first two or we add the second and third, it doesn't matter how we go about that. Okay, so let's, once again, we'll give ourselves some elements to work with, right? So let's let A be in 5z, B be an element of 5z, and C be an element of 5z. Okay, we've got our A, B, and C to work with. And then we would like to add those up. So A plus B plus C. And what we need to show, so I'll write here, we need to show that A plus B plus C equals A plus B plus C, like so. Okay, and once again, it's going to help if we frame it. If we frame each of these here, A, B, and C, as elements of 5Z. Okay. Yeah, let's try that. Okay. Yeah, so what we'll do is we'll say, you're exactly right. So A equals, say, something like 5D. B, we can say, is 5 times. In a full write-up proof, what we would like to say is that sort of comma here, D is an element of the integers, E is an element of the integers, and F is an element of the integers. And that's just to clarify. In any proof, it's best to make sure that you define anything that you say. That way anybody that reads it isn't left sort of wondering, right? Okay, so now we have that. Let's try to rewrite this here. So we'll say 5D plus 5E plus 5F. And we need to show that these parentheses here won't matter which way we're adding those. Okay, so let's go about that. I know that this equals, factoring out this 5 here, so I'm factoring out that purple 5 from these. And then I'm left with parentheses D plus E, and then plus of 5F, like so. Okay, and then from there, remember where we're trying to get to is to show this right here. Okay, we just have to make sure that we can move those parentheses around. So let's continue on, see how we may be able to do that. I know that this equals, if I pull the 5 here and the 5 here, if I factor those out now, I've got a 5. Now I'm going to add some brackets because we're going to end up with sort of multiple parentheses happening. 5 times D plus E in parentheses plus that F. Okay. And then now from here, what I can do is say that, and I'll put this in, let's say orange here. This here, these are elements, let's say elements of Z. And we know the integers have the associative property. So what I'll say is I'll apply the associative property of the integers Okay, and then what that's going to give me will be 5, and then in these square brackets here, D plus E plus F. Okay. And then now from here, it's simply a matter of sort of going back the other way. And now we just have to make sure that this, we can sort of shape to look like this here. This A plus B and C in parentheses. So that's what I'll do now. Now I'm going to distribute this 5 to both sides there. Okay, and then I'll further distribute this 5 to the E and F. And now we're pretty much done. So I'm going to take one more step here, and that's just to turn this 5D, the 5E, and the 5F back into the form that we would like to work with. Okay, so that's going to be A plus, in parentheses, B plus C. Okay, and looking back up here, that's exactly what we wanted here. So again, I'll write a box, shade it in. And that means that we've shown associativity. Okay, and then the this third property here, identity, so now we want to show that we have an identity element. And a lot of times when we want to show the identity element, we typically show exactly what it is. So we're going to actually find that element. Now sometimes you can prove it by showing that one exists without knowing what it actually is. In this particular case, we're actually going to use the identity of the integers and apply it here. Okay, so I'm going to say let. All right, so let, we need some elements to work with here. So I'll say A, B, and 5Z. And here now what I'm going to do is I'm going to say I, B, and 5Z. So this will be our identity. But what I'm going to say is that I equals 5 times 0. So we'll take 0 being the identity of the integers, which really we can shorthand write 0. Okay. And then what is it that we need to show for the identity? So really we would like to show that A plus I equals to I plus A, which equals to A. So it turns out even if you don't have a commutative group, the identity you require to be commutative. And this is what I mean by commutative, is that we can apply the operator in any order from the left or the right side. So A plus I is the same as I plus A. Okay, so now let's work that out. So we have A which I'm going to let, in this case, once again, I'll say a equals 5, let's say 5 times d again, right, where d is an integer. Okay, and then what I'll do is I'll add that. So I'll say 5d plus I, but 5d plus I, well, we said that I is really 5 times the identity of the integers, so 5 times 0. Okay, but then this is really 5 times d plus 0. All I've done is factor out this 5 here. And then in orange here, what I'll do is I'll show now d plus 0. We know that 0 is the identity of the integers, and so what we can say here is this is really equal to d, because we know this about the integers. And that allows me to say that this is equal to 5d. Okay, so that's part of it. Now we have a little bit more to do here, because we want to show not only that this 5d plus I, or this a plus I, right, equals a, we also want to show that it's equal to adding it in the opposite order, right, or flipping the a and the I. So here's what we'll do there. I'll take this 5d, and I know 5d to be equal to 5 times d plus 0, right, I'm sort of going backwards now, d plus 0 that we had here. But I know that the integers have the identity 0. And so I know that I can flip those now. I can do 5 times 0 plus d. And that's a property of the integers in general. And now we have 5. I'll distribute out the 5. So 5 times 0 plus 5 times d. But we know 5 times d is a, so 5 times 0 plus a. And then this 5 times 0 here is I plus a. And what this does is this shows us that a plus I is equal to a, but it's also equal to I plus a. I'll draw my box, so that gives us identity. And then now there's one more property to show. So now we have, we've shown closure, associativity, identity, and now we've got inverses. Okay, so the fourth and last thing we need to show, inverses. And you can sort of see the pattern here. We're going to again leverage what we know about the integers in order to show something about the set 5z. Right, so we're going to leverage information from the integers. Okay, so let's give ourselves some elements to work with again. Now what we'll do is we'll say let let A be in 5Z. And then what we'll do is we'll let A inverse, so we'll say that there's an element A inverse in 5Z, but what we're going to do is we're going to allow A inverse to be defined like this: 5 times, let's say D inverse, where D is an element of the integers. And then D inverse is simply the inverse element of that element D in the integers. And we know this exists. So I'll say we know D inverse exists because Z is a group. And I'll write in parentheses under addition, right? So now all we have to do is we need to show that this, so defining it this way, gives us the properties that we want. Okay, and here's what we'll do, is we'll say A plus A inverse. And then what we've got to do, so I'll make note here that A equals 5 times D, right? A plus A inverse will take those forms there, 5D, and then A inverse we said was 5D inverse. And that same trick we used where we factor the 5 out, we'll do that again. So factor out the 5, and now we have D plus D inverse in parentheses. And then this is going to give us that nice trick again where we can kind of fall back on what we know about the integers. Okay, and we know about the integers that if you add an element and its inverse, it's going to give you the identity. So it's going to give you 0. And in this case, we have 5 times 0 there. And this is exactly the identity of the set 5Z that we showed in part 3 of this proof. Okay, and that's all there is to it. So that shows us that we do have inverses. We showed how we define it up here. And we showed that it upholds that property, right? And now, so now that we showed all 4 of these things, so we showed closure, we showed associativity, we showed, let's see here, identity, and then we showed inverses. Okay, and then all we have left is to just reiterate. This shows that 5Z is a group under addition. Okay, and then at the end here, we'll write one more box just to show that the proof as a whole is completed. Okay, and so that is the process that we'd like to go through each time that we show a set to be a group. Now the operation in question may change, as well as the way that we go about showing these properties. but the routine of going through those pieces remains the same. Okay, and then for some additional practice problems, what I would recommend so for practice here, let's say 1. So let's say prove or disprove. Let's take the same example. 5z is a group under subtraction. Whereas before we just showed that it's a group under addition. Now let's look at subtraction. Okay, so that would be a good one to look at. And then let's see something else here. So that's A. And then part B, prove or disprove. 5z is a group under multiplication. Okay, so using the operation of multiplication. And looking at those two examples helps to sort of solidify this idea of groups, and it gives some good practice with going through these properties and showing these properties to be true. Okay.